Hey everybody, it's Wednesday, January 20th, and as you can see here in the aim today, our goal for today's video is to pick right back up where we left off with our conversation on conservation of mechanical energy. Now, the first thing I want to actually do in this video is review the problem that I asked you to submit from yesterday's video. So in yesterday's video, if you remember, there was a problem at the very end, an extension on the actual problem we solved, which basically asked you to apply conservation of mechanical energy to that situation from the question in the packet. Now, the first part of it I solved, which was that first bullet point there. What will be the maximum speed of the rock if the slingshot is stretched 15 centimeters to launch a 0.2 kilogram rock? The second part of the question asked if the slingshot was oriented straight up in the air, what will be the maximum height of the projectile? And so, just as a general reminder, this was the situation. They said the force required to stretch the slingshot by different amounts is shown in this graph. Here's the graph. And then the question said to find the spring constant, which we did, which was 400 Newton meters. And we said you could either do this by finding the slope or just by using the equation F equals kx. Either way, we get a spring constant of 400 newtons per meter. And then the second part of it asked us to find the amount of elastic potential energy, or the amount of work done when the slingshot was stretched to this distance of 15 centimeters. Then we went ahead and said if the slingshot is stretched that much, we could determine its speed by saying the initial elastic potential energy is equal to the kinetic energy and then solving for the speed. And this particular question here, the second part of it, asked you to determine the maximum height of the projectile if it was shot straight up in the air. The main point that I made before I told you to go ahead and solve this problem was that the gravitational potential energy was relative because there's no such thing as absolute height. This means that you can choose where the height is zero. And so the main point of that instruction, which I hope you all realized, was that when you are shooting something up in the air, like so if the slingshot is located here, you should make the lowest point in the system zero. So when the slingshot is here and the thing is stretched another 15 centimeters, you have a lot of options to, in terms of where you're going to choose to make the zero height. You can make the zero height here and then say that the rock is below that, but that doesn't really make much sense. The most appropriate thing to do is to just say the lowest point in the system, that's where y equals zero, and then base all of your height measurements on that choice. And so that is the idea behind the problem. That is what we are going to do. And so the solution to the problem here would look a little something like this. So the first thing that we're going to do is we're just going to make our list of knowns. So we were told here that the mass of the rock is 0.2 kilograms. Of course, we know G, which is going to have to be used in this problem, is 9.8 meters per second squared. We were told that the slingshot was stretched 15 centimeters or 0.15 meters. We solved for the spring constant in the beginning part of the problem and found that that was 400 newtons per meter. And we're looking for the height, which we'll mark as delta y. And so the basic conservation of energy statement behind this problem is that the initial elastic potential energy stored in the system is equal to the final gravitational potential energy. And then once we have that, the rest is algebra. We sub in the equations for both of these types of energy. So the elastic potential energy is 1/2 kx squared. The gravitational potential energy is mg delta y. And all we have to do to solve this for the height is divide both sides by mg. And so that would give us kx squared over 2mg. And that's it. The rest of this is just like a pretty much a straight up plug-in problem. So we plug in the spring constant, 400 newtons per meter. We plug in x squared, which is 0.15 meters. And then, of course, we got to square it. So we put parentheses around it. And then we divide by 2 times the mass, which in this particular problem is 0.2 kilograms, times g, which is, of course, 9.8 meters per second squared. And of course, if you didn't want to put the 2 in the denominator here, you could have put 1/2 in the numerator. That is the exact same thing. And when you do that math, plugging in all those numbers, making sure you have all of this done correctly in the calculator, you get 2.2959 meters, which to two significant figures, that's what the only number given in the problem was really, we can put at that as 2.3 meters. And that's it. Now, there are a lot of ways that you could have solved that problem. In fact, since you already calculated the speed, you could have said the kinetic energy that this thing has once it is launched by the slingshot ends up being equal to the gravitational potential energy. We do have a little bit of problems here because the place where this object has its initial kinetic energy, if this is the slingshot, is here, and the place where it has the elastic potential energy is 15 centimeters below that. That's an important point. We're not going to go too nuts about that. 15 centimeters is not an enormous amount of this distance here. It's only about 7%. Obviously, that makes a difference, 7%, but it's close enough. But it's important to realize as this thing rises, it's losing that elastic potential energy, it's gaining that kinetic energy, and this object, from there on, once gravity is the only force acting on it, experiences that loss in the kinetic energy as it turns to gravitational potential energy. Really, a more accurate, like the most accurate analysis of this that you can do is to account for the fact that the object rising here 15 centimeters is actually also giving you some gravitational potential energy increase. And so that means it's not going to be going as fast here as opposed to if we just shot the thing horizontally. But the main point that we want to make here is by just considering the initial state and the final state, we actually sort of get around having to think all that hard about what happens in between. And that will always be a good way to solve these problems. And with that, that's it for that problem. Now, the main focus of today's video is going to be to answer a bunch of questions on a worksheet. But before we get to that, there's just one kind of straight up mechanical energy conservation problem that we have not taken a look at. And so I want to show that to you first and just write one quick note about it and then see, sort of how that note plays out in an actual problem. And then we'll just go straight into the worksheet. So the kind of problem that I'm talking about, which I would like us to write a note for, is a problem that looks like this, generally referred to as the roller coaster problem. So it says here, a roller coaster cart shown in that figure is pulled up to point 1 where it's released from rest, assuming no friction, calculate the speed at points 2, 3, and 4. Now, this is a basic conservation of mechanical energy problem. By virtue of the fact that the object has some height, it has gravitational potential energy, and as the object rolls along the track, basically what we have is this constant conversion between gravitational potential energy and kinetic energy. That's how roller coasters work. They usually, if you've ever been on a roller coaster, they have like a chain lift part of it that basically just literally tugs the cart up with a chain, and then basically it's a gravity machine the rest of the way. But here, there are a couple of points to be made about this problem. It's very important to realize that the ground here is not what you would call y equals 0, because the ground has no relevance in this problem at all. This problem, especially with like these diagrams here, is really trying to make the point that the heights are all measured relative to this location, this line here along the bottom. And notice that line also happens to be the lowest point in the system. And so that's the place where we would consider that y is equal to 0. This is what we meant here by this note. There is no such thing as absolute height. This means you can choose where the height is 0. Now, you could make the height 0 down here, but that is not going to make the problem easier for you. The easiest place to say this is where the height equals 0 is generally going to be the lowest position occupied by the object. That is almost always the best and most straightforward way to go over the problem. Now, there is a very significant difference between point 2 and points 3 and 4. If we acknowledge the fact that it makes the most sense to consider y equals 0 to be here at that horizontal line where all the heights are measured from. And the obvious difference between those points here is that at point 2, all of the potential energy the cart had has been converted to kinetic energy. But that's not the case at points 3 and 4. At points 3 and 4, the object has some height. Because the object has some height, it has some gravitational potential energy there. And so what we want to talk about here are some smart ways to do this problem. What I refer to these problems as is I refer to them as incomplete energy transfers. Every single problem we've looked at so far, we have seen what I refer to as a complete transfer of energy, meaning whatever kind of energy was present in the system in the beginning, all of that has turned into another kind of energy. So like when we took an object and we dropped it, we said it's going to lose all of its height, and all of that gravitational potential energy associated with that height is going to turn in to kinetic energy. Now, whether you realize it or not, we actually did look at one of these incomplete energy transfer problems already. This was the problem where a baseball was thrown up and it landed on a roof at some height. Now, we solved that like the long way, and I'll remind you about this sort of, or at least by showing you the same technique if you forgot. But that is an incomplete energy transfer because the object started off with kinetic energy and it still had some kinetic energy at the end. It also had gravitational potential energy. So there are a couple of ways that you can go ahead and solve those problems. But my main advice here is when the energy transfer from gravitational potential energy to kinetic energy is incomplete, there are two ways we can solve the problem. Always, we set the initial energy in the system equal to the final system energy, and that's the way we did that baseball problem. We just said, what kind of energy does it have at the beginning? What kind of energy does it have at the end? And then we set those things equal to each other. Or we can set the change in gravitational potential energy equal to the gain in kinetic energy. And that is a very important point. So take a second to pause this video here and write that down, and then we will revisit that roller coaster problem where I will show you exactly what we mean by that. Okay, so in this roller coaster problem here, they've asked us to calculate the speed at points 2, 3, and 4. We're just going to go ahead and skip it for points 2 and even point 3 because it's a fairly straightforward problem. And I have a feeling once you see the example for point 4, you will find that this isn't all that difficult. But at the very least, we should at least talk about how to solve 4, talk about what we mean by this new approach with the incomplete energy transfer idea, and then we'll move on. So the first thing we should say here is that when this object is at point 1, it has the maximum gravitational potential energy it's going to have. And so we can say here that the loss in gravitational potential energy from 1 to 4 is going to manifest itself as kinetic energy. And so the first thing we'll do is we'll just make a list of knowns here. We are going to say that G, of course, is 9.8 meters per second squared. Now notice they do not tell us the mass of the roller coaster cart, but you should know by now, having solved some of these conservation of energy problems where it goes from potential to kinetic, that that's not going to matter. Now what we need is the change in height that this thing experiences. And if we go back to the diagram, we can see this thing starts at 32 meters and it ends at 0.4 at 14 meters. So the change in height is 18 meters. And that's the important feature here. And then what we're looking for is the speed. And so basically the way that we set this up is that we say the change in gravitational potential energy is equal to the change in kinetic energy. And if we just write here, once again, delta UG equals K final minus K initial, If you recognize the object started from rest in the beginning, then there is no initial kinetic energy. And so that means the final kinetic energy here equals mg delta y. Now, of course, they asked us not for the final kinetic energy, but for the final speed. And so we'll write 1/2 mv squared equals mg delta y. And of course, as we expected, the masses cancel. And so what we're left over with is a familiar looking expression, 2g delta y. And so if we plug in our numbers here that we have for this particular problem, we have 2 times 9.8 meters per second squared times 18 meters, and that gives us an answer of 19 meters per second. And that's really it. Notice that's a nice, simple, neat little way to solve the problem. The alternative, which, to be clear, this is what I meant by number 1 in this list, we could set the initial energy equal to the final energy, is, in my opinion, a little longer, but that doesn't even really matter because it leads you to the same result. The way that you would do it in this instance, where you literally just set the initial energy equal to the final energy, is you say this thing's got gravitational potential energy in the beginning, and then at the end, it's got kinetic energy and potential energy. And then just go ahead and solve it. So you would have mg delta y1, like the initial height, equals 1/2 mv squared, final for whatever location it's at, and then mg delta y2, or final. You can make that final and actually make this initial if you want, just to be consistent with these symbols. Notice the masses will cancel, which is what you'd expect. So you would basically just have g delta y naught equals 1/2 v final squared plus g delta y final. And then notice here, when you went and solved this for v final, you would get v final. Let's actually just do it for v final squared first so you can see it. You would have to subtract the gy final to the other side. So you would have, or let's actually just leave the half in there too. You would have g delta y naught minus g delta y final. And notice both of those terms have a g, so you would factor it out. And the important thing to realize is, because you're subtracting the heights, the number that you're going to get there is going to be the 18 meters we had over here. And so the point that we're trying to make here is that that's the same thing. It's just a little bit longer to arrive at that expression, a little more writing. You do it however you feel comfortable. That said, in my view, for problems like this, which are going to come up from time to time, but not so much, this is an easy way to do it. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at some problems on a worksheet. So attached to today's post on Google Classroom, there is a worksheet entitled Work, Energy, Energy Conservation, and Power Problem Solving Worksheet. And I'd like you to go back and open up the attachment for that now if you haven't already. And basically, I just want to go through all of the problems on this worksheet. I'm going to ask you to pause this video quite often to go ahead and do the problems, because at this point, I shouldn't have to show you how to do them. I'm really just going to ask you to pause, give you the opportunity to do them, and then we'll go over them here in this particular video. Some of these are a little challenging, and so I don't want to just leave you to do it by yourself and then go over it tomorrow. So the first problem, which I've included in this slideshow, says a 1.5 kilogram cart released from rest at the top of a smooth incline has a gravitational energy of 6 joules relative to the base of the incline. Notice there is no such thing as absolute height, so there is no such thing as absolute gravitational potential energy, and this is why it says relative to the base. The base of the incline is the lowest point that this cart is going to reach, and so that's where we are considering our zero to be. Part A of this worksheet is asking you to calculate the cart's speed at the bottom. Take a couple minutes to pause this video here and work out the speed at the bottom. And when you hit play, we'll go over the solution. Okay. So in order to calculate the speed of the cart at the bottom, you need to recognize that this number given here in the beginning, 6 joules, is your initial gravitational potential energy. They told us that the mass of this cart here is 1.5 kilograms, and we're looking for the speed. The basic conservation of energy framework we're dealing with here is that the initial gravitational potential energy is equal to the final kinetic energy. Now, we already know the initial gravitational potential energy, so we're not that concerned with that. So that just means we have 1/2 mv squared. Notice I'm just switching these things on each side of the equal sign. 1/2 mv squared equals UG naught. And that means that V is going to be equal to 2 UG naught over M. And so we have here 2 times 6 joules over 1.5 kilograms. And of course, all that's under the radical. And so when you do that math, you get 2.83 meters per second. And that's it for part A. It's pretty straightforward. Now, I just want to be clear about one thing. In years past, I have seen students take that gravitational potential energy number, 6 joules, use the equation mg delta y to determine the height, and then sort of set the problem up like mg delta y equals 1/2 mv squared, that kind of deal. It's important to realize that's the same thing, just longer. So this approach works. You already know the value for the initial amount of energy, so you can just leave it like that. It's a perfectly reasonable, acceptable way, and obviously the most efficient way to solve this problem. This part of the problem, though, like I mentioned, is fairly straightforward, is not really the point of this problem being included on the sheet. There are nice conceptual questions that accompany the situation afterwards. And so now I want to take a look at part B. Part B here says when the cart has rolled halfway down the incline, the cart's gravitational potential energy will be greater than 3 joules, less than 3 joules, or equal to 3 joules. Take a minute to pause this video here, think about the situation, come up with an answer, and try to use an equation to justify your answer. And when you hit play, we'll go over it. Okay. So this question says the cart has rolled halfway down the incline. And they're asking us about the cart's gravitational potential energy when this thing is halfway down the incline. Now we can say here that this whole solution comes down to the equation. The gravitational potential energy is directly proportional to the object's height. UG equals mgy. I'm leaving out the delta for now just because it's annoying to type. So the gravitational potential energy is directly proportional to the object's height. When the object is halfway down the ramp, the height of the cart is half of the original height, which means the gravitational potential energy is half of its original value, giving a new value for the gravitational potential energy of 3 joules, making the answer choice C. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, let's take a look at part C. Part C of this question says, when the cart's rolled halfway down the incline, the cart's kinetic energy will be greater than 3 joules, less than 3 joules, or equal to 3 joules. Take a second to pause this video here and come up with an answer. Justify your answer using some principles of physics. And when you hit play, we'll go over it. Okay, so pretty straightforward answer to this question here. We already answered in part B that when the cart's rolled halfway down the incline, it loses half of its potential energy. And so the obvious question here is, well, where does that potential energy go? It turns into kinetic energy. So what we can say here is since the kinetic energy of the cart is obtained from the conversion of gravitational potential energy, and then we'll just write in parentheses here, to kinetic energy, if the gravitational potential energy halfway down the incline is now 3 joules, and the remaining 3 joules of total energy are left as kinetic energy. And that's it. It's a basic conservation of energy problem. When the object is halfway down the ramp, 3 of the 6 joules of initial total energy are converted to kinetic energy, and 3 joules are left over as gravitational potential energy, and that's it. Take a second to pause this video here and write that down, and when you hit play, we'll move on to part D. Moving on to part D. Part D says when the cart has rolled halfway down the incline, the cart's speed will be half its speed at the bottom, greater than half its speed at the bottom, or less than half its speed at the bottom. Take a second to pause this video here, think about this one, try to come up with an answer and a justification, think about the equations, and when you hit play, we'll go over it. This problem is not as straightforward as the others because you have to do some thinking about the relationships told to you in the equation. The situation that we've said here is actually not so complicated thus far in terms of the energy amounts. We said the gravitational potential energy is 6 joules at the top. And that means all the way at the bottom, all of that energy is turned into kinetic energy. So the kinetic energy at the bottom is 6 joules. And so what we can say here is that in the middle, the gravitational potential energy is 3 joules, and the kinetic energy is 3 joules. That's it. It's pretty straightforward. The speed, on the other hand, is a bit of a different story because there is not a direct relationship between the speed and the kinetic energy like there is between the height and the gravitational potential energy. The reason why the gravitational potential energy halfway down the ramp gets cut in half when the height gets cut in half is because they're directly proportional. But unlike the direct relationship between the gravitational potential energy and the height, the kinetic energy isn't directly proportional to the speed. It's proportional to the square of the speed. And that is a big and important difference. And so essentially, the proper way to think about this is not necessarily that the kinetic energy is proportional to the speed squared, but that the speed is directly proportional to the square root of the kinetic energy. Because thinking about this as a 1-1-1 rule problem will give you the proper answer. Because notice, if we say here that originally, or at least at the bottom of the ramp, the speed is 2k over m, well, halfway up the ramp, the kinetic energy is half of this 6 joules. It's 3 joules. And so thinking about this like a 1-1-1 rule problem, we would say, well, this v prime is 2 times half k over m. And so that means here that v prime, pulling out that square root of 1/2, keeping in mind that this is under the radical, so we have to pull it out as a square root, it would give us v prime equals the square root of 1/2 times root 2k over m, which means that v prime is going to be the square root of 1/2 times v. If you're confused about that, it's very important to remember how square roots work mathematically. The basic principle is that the square root of the products is the product of the square roots. So to put it in a little bit of a simpler version here, we would say that the square root of a times b is equal to the square root of a times the square root of b, right? So that means here, this whole mess under this radical really is the square root of 2 times the square root of 1/2 times the square root of k over the square root of the mass. This is what we're pulling out, which leaves behind root 2 times root k over root m, which we can then recombine like that. So the basic idea here is as follows. When the object goes from the top to the bottom, the total 6 joules of gravitational potential energy is converted to kinetic energy. 6 joules of gravitational potential at the top means 6 joules of kinetic at the bottom. Those are the facts. So, halfway down the ramp, because the gravitational potential energy is directly proportional to the height, when this height gets cut in half, because the object is at the halfway point down the ramp, the gravitational potential energy gets cut in half from 6 joules to 3 joules. Because energy is conserved, that 3 joules of gravitational potential energy that was lost gets converted into kinetic energy, meaning at the halfway point, there's 3 joules of kinetic energy. So far, all of this stuff is true because of the direct relationship between the gravitational potential energy and the height. However, the kinetic energy is not directly proportional to the speed. the kinetic energy is directly proportional to the speed squared. And so that means even though this thing has gained half of its total amount of kinetic energy, it's going to have greater than half its speed at the bottom, because the square root of 1/2 is 0.707, meaning at the halfway point, it's actually going to be at approximately 71% of V final. And so what we can say here, and we'll write this down as our explanation or our justification for this question, is we'll say using the equation k equals 1/2 mv squared, we can see that the speed of the object is directly proportional to the square root of the kinetic energy. Using the equation for speed, when the kinetic energy is half of its final value, speed is, well, square root of 1/2 its final value. And I'll write here 0.707. Notice if you actually just plug in 3 joules into the kinetic energy equation with a mass of 1.5 kilograms, you'd find that the speed of the object when the kinetic energy is 3 comes out as 2, when the final speed is 0.283. That's the deal. Take a second to pause this video here and write that down, and when you hit play, we'll move on. Okay, now before we move on to the last part of this worksheet, I want to just take a minute to talk about why this makes sense. Because if you really think about this answer here, it does make a good amount of sense. And since we've already kind of said everything that we could say about the energy analysis, I think it's probably good to go back and rationalize this in terms of dynamics and kinematics. And so if we have an object on the top of this ramp here, this thing is an inclined plane. And if there's no friction, then that means the acceleration is just going to be g sine theta. You can work this out if you use the inclined plane equations. And so that tells us that this thing is going to have a constant acceleration the whole way down. And the point of interest here is going to be this midway point. Now, the interesting thing about the midway point and the way that helps us make sense of this problem is that the displacement from the top to the midway point is the same as the displacement from the midway point down to the end. So the idea here is pretty straightforward. This object is starting with an initial velocity of 0, and it is going to make it down to this midway point after going this displacement. And so it's going to take a certain amount of time to do that, right? And because the initial velocity is 0, that amount of time is just going to be whatever the velocity is here divided by the acceleration, which is going to be g sine theta in this case. However, because at the midway point now, the initial velocity for the second half, which I'm just going to call v naught prime, is going to be the final velocity from the first half of the trip, this object is already moving at a pretty good speed by the time it reaches this midway point. And so it should make sense to everybody that in order to travel a certain distance, it's going to take less time if you start with a non-zero initial speed than it does if you start with an initial speed. And so the point here is, because this distance is traveled in less time, the acceleration doesn't act for as long. And the whole idea is, if the acceleration doesn't act for as much time, it's the same acceleration, but if it's a smaller amount of time, then we're going to have a smaller change in speed over that second part of the distance. And so what we see when we use the energy analysis is that from the beginning to the midway point, the object reaches 0.707 of the final velocity here. And so it does about 70% of the acceleration during the first half of the distance, and it does about 30% of the acceleration over the second half of the distance. The reason why is because even though the distances at the top and the bottom are the same, the times are not. And that's the important point here. Take a second to pause this video here and write that down. And when you hit play, we'll move on to part E. Okay, part E, the last part of this first problem here, says a 1.0 kilogram cart is released from rest at the top of the same incline. At the bottom, it will be moving faster than the cart, slower than the 1.5 kilogram cart, or at the same speed as the 1.5 kilogram cart. Take a second to pause this video here and think about this one. Try to come up with an answer and an explanation. And when you hit play, we'll go over it. So this problem is pretty straightforward. And because it could be potentially confusing, despite the fact that it really is pretty straightforward, they ask about this sort of issue a lot on the AP test. The answer here is C, the same speed as the 1.5 kilogram cart. The easiest way to justify this answer is to think about the actual energy transformation that happens with a cart on a ramp. The actual energy transformation that happens is a transformation of gravitational potential energy to kinetic energy. And the way that you would actually solve that is by taking the two equations, mg delta y for the gravitational potential energy, and setting it equal to 1/2 mv final squared for the kinetic energy. And what you should notice, since there is a mass term on both sides, it cancels. When you solve this for the speed, you get 2g delta y. What that equation shows is the final speed of the cart is not dependent on the mass. Let's go ahead and write down that explanation, and then we'll talk about some of the things that confuse people about this one. The explanation here is going to be pretty straightforward, though. We'll just say here, when gravitational potential energy is converted to kinetic energy, there's no mass dependence, as all objects in the Earth's gravitational field accelerate at the same rate, so the mass cancels. That's it. Take a second to pause this video here and write that down, and when you hit play, we'll move on. The basic idea we can say in a large number of ways. It all comes down to that argument about inertia and the gravitational acceleration. The point is, an object with less mass does have less inertia, and so it is easier to move, which would make you think maybe that it's going to have a higher final speed. But since gravity is going to be pulling on it with a smaller amount of force, it's actually sort of has that cancellation effect. A lot of people end up thinking, because this problem told you the thing has 6 joules of gravitational potential energy in the beginning, a lot of people end up thinking, well, the equation says gravitational potential energy equals mg delta y. And so if this object has less mass, well, it's going to have less potential energy in the beginning. That is a fact. If the 1.5 kilogram cart has 6 joules of gravitational potential energy at the top of this ramp, the 1 kilogram cart surely will have less than 6 joules of gravitational potential energy. That is an incontrovertible fact. It'll have less initial energy. And since energy is conserved, because there's no friction here, the mechanical energy is conserved, the object is going to have less final kinetic energy, because the kinetic energy comes from the gravitational potential energy in the beginning. But the fact that the object has less kinetic energy is not a problem for the final speed, because even though it has less kinetic energy, it's going to have less mass. So it has less kinetic energy, which might make it seem like it's going to move slower, but the fact that it has less mass means that energy can be used to make the thing reach the initial speed. It's easier for the energy to move that mass, so to speak. And that's the idea. Now, you might have noticed there are 2 other problems on the back of this worksheet, but because this video is already getting a little long, that's going to be it for today's video. In the very beginning of tomorrow's video, we're going to get into the last 2 problems on this sheet. And with that, that's it for today. Have a good one, everybody.